Well, say you have n pigeons and you have n minus 1 pigeonholes, and then you put all the pigeons in holes. Now, there are not enough holes for all the pigeons for it to be one pigeon, one hole. Can't. There's not enough holes. So therefore, there must be at least one hole that has 2 pigeons. Well, it has more than one pigeon. Okay? That's the pigeonhole principle, and it applies here. Okay? And the pigeonhole principle is basically common sense. Okay? So here, so if you have p pigeons placed in less than p holes, at least one hole has more than one pigeon in it. Yeah, just common sense. All right. All right. Now have a look at this figure. Now remember, what are we trying to do? We're trying to prove. This is sort of the overview, the proof idea. We're trying to prove, well, give the idea of the proof of the pumping lemma. Right? So we're heading towards showing that the string can be split into 3 parts, x, y, z, such that those x, y, z satisfy the 3 conditions. The critical one being that x, y pumped, in other words, y to the I, I copies of that y substring, so that x, y, I, z, those 3 parts, also belong to the language. Right? Now that's where we're headed. Okay. So here's your string that we're talking about, S. Right? There's the first symbol, the second symbol, to Sn. We assume the length of this string was n. Right? In other words, n symbols by definition. Okay. Now, as each symbol gets read, that will call, it's a DFA, let's say, and that means that the state will change as a result of reading the symbol. So, so what you've got here now is the sequence of states. Time is going that way. So this is now the sequence of states that your machine M goes through, reading each symbol in your input stream one by one. Right? Time going that way. So the initial state, it starts off at Q1, then it reads symbol, the first symbol S1, and as a result of that, transition table, transition function tells the machine the next state should be of the machine should be Q3. Then it reads the second symbol, and the transition table tells the machine the next state should be Q20, and so on. And then Q9, Q17, let's say Q9, Q6, Q35, Q13, the accept state. Now I've circled Q9. Now remember the previous discussion. There must be a repeat state, right? In that sequence, well, this sequence here, and there will be n plus 1 states, a sequence of states, n plus 1 of them. And there will be n symbols here, okay, in your string. The first symbol, the second, in your string of n symbols, length n. Right? Now let's say then there has to be one of these, at least one of the symbols here has to be repeated. Okay, more than one. Well, let's say it's Q9, and let's say it was only repeated once. Okay, so they're all different except these 2, let's say. And okay, now so you have a repeat. So let's say let's have this sequence or subsequence of states. Let's call that X. And starting with the repeated and ending with the repeated state, so it's Q9, let's call from here to here, call that Y. Right? And then from here to the end, call that Z, that region. So I've got 3 parts, 3 how can you call it? subsequences, I guess, right? That would correspond to your x, that would correspond to your y, and that's tz. Well, actually, strictly speaking, let's split. Well, it's corresponding, but let's split the string actually, because it's the string we have to split into x, y, and z, not the sequence of states. All right. So which part of it is x? Like, where's the dividing line? That's the critical part. You know, where's the dividing line between x and y, and between y and z? Okay. So we're dividing this now into three pieces, x, y, and z. Okay. So piece x is a part of x, a part of s, appearing before Q9. All right. Before Q9. In other words, it's this. Right. S1, S2, S3. That's your x. That's your x part of your string. Alright. Now piece y is the part between the two appearances of Q9. So I guess that's S4, S5. Right? Okay? So piece y is the part between the two appearances of Q9. Well, here's Q9, between here and here. So it's S4, S5. And S6 onwards is Z. Okay? So effectively, X, that's the first part of your three-part string, S. So X, what's it doing in terms of states? Well, it's taking the machine from Q1 to Q9, right? Because this, the third symbol here will take you from state Q20 to Q9. So this X here, this substring, S1, S2, S3, will take the machine from state Q1 to Q9. Okay? And Y will take the machine from Q9 to Q9, right? Via S4, S5, these two symbols. Okay? And Z will take the machine from Q9, from here, to the accept state Q13. Right? So that's your Z, S6 onwards. That's your Z, these two. Between the repeat states, these two, S4, S5, that's Y. And what's left that way? That'll be X. So X, Y, Z. And you split the string into X, Y, Z according to the state that got repeated. Okay. All right. So that's represented this way in terms. If you now look at the sequence of states here, and it's sort of represented figuratively here. So your X corresponds to transitioning from Q1 to Q9. Right, that'll be your X, corresponding to your X, and then these dots, they correspond to states. Right? So you imagine a sequence of states. So you go from Q1 to Q9, and then the Y here, these will take you back to Q9. Right? So you've got this sort of looping dotted loop here, labelled Y. They're the symbol. Well. This dotted line here is the sequence of states that from Q9 back to Q9. So in this case it'll just be Q17, there's only one for here. And Z, that'll be a sequence of states going from Q9 to Q13. So Q6 ... Q35, Q13. Right? Well, we've run out of board. So we're just getting into the nitty-gritty. Well, are we in the proof yet? No, we're still in the proof idea, so we haven't started the actual proof yet. But you can probably sense the direction of the proof, right? We prove that there has to be repeats, and we use the positions of the repeats as the boundaries between x and y and z. Okay, and so we will use this to progress further in the proof of this pumping lemma.